Class by Raj, teaching for Physics Semester 2. Magnetic field due to current. Today we are going to look at example of magnetic field due to current for three examples. Current that is in a straight wire, current in the circular loop, and current in the solenoid. For example, for a straight wire, the learning outcome will be to state the Ampere's law and use the law to derive the magnetic field of a straight wire. Magnetic field due to current in a straight wire. Alright, so I have a straight wire here, and the straight wire is carrying a current. There's a current flows inside the straight wire. Okay, so when there's a current flows in a straight wire or in a conductor, there will be a magnetic field produced around the wire. Okay, alright, so the magnetic field will be produced around the wire. So now magnetic field. So let's talk about the magnetic field. Now when we talk about the magnetic field class, first let's look at the pattern of the magnetic field. The pattern of the magnetic field are concentric circles. Okay, they are concentric circles. Okay, they are concentric circles. So if I draw here, they will look something like this. Okay, they will look something like this. Okay, these are the patterns. Okay, the separation between the line of forces, these are the magnetic field line of forces. The separation between the line of forces, this is the separation, increases. Okay, increases as the distance from the wire increases. As the distance from the wire increases, the separation between the line of forces increase as the distance from the wire increase. So this means that the field is getting weaker as it goes away or further from the wire. Okay, the field is getting weaker as the distance from the wire increases. Okay, so this is the pattern of the magnetic field around a conductor. Okay, a straight wire. Now let's look at the direction of the magnetic field, because we know a magnetic field is a vector. So it has a direction, it has a magnitude. So let's look at the number 2 is the direction of the magnetic field. Okay, now the direction of the magnetic field is determined by using a right hand grip rule. We use what? We use right hand grip rule. Okay, now we take out our right hand. So this is the right hand. The thumb will represent the direction of the current. Okay, the thumb, this is the thumb, this is the fingers. Okay, you grip it like that. Okay, so the thumb will represent the direction of the current, and the fingers will represent the direction of the magnetic field. So in this example here, if you see, the thumb will represent the direction of the current. So the current is in this direction. So my fingers is representing the direction of the magnetic field. Okay, so if you see like that, it's like as if it's going into the page. So the direction of the magnetic field will be such. Okay, it will be in that such direction. Okay, so this is called as the right hand grip rule. Okay, now let's talk about the magnitude of the Okay, now let's talk about number 3. Number 3, let's talk about the magnitude of the magnetic field strength. No. Magnitude of the magnetic flux density. Which is the B. Okay, the magnitude of the magnetic flux density, you have to use Ampere's law. Ampere's law. It is defined by Ampere's law. So let's look at our textbook. Okay, Ampere's law. Now, Ampere's law says what? It says that for any closed path, the sum of the length element delta L, okay, times the magnetic field parallel to the element equals to, okay, so what does it trying to say? All right, sum, Ampere law says sum of the length element, okay, times with the magnetic field parallel. So B parallel times with sum of the length element. Okay, so when it says the word times, we just put in the form of like this. Okay, so B parallel to delta L. That means, class, now let's take a small portion of this place here. This portion here. Okay, so this is delta L. Delta L. Okay, so at this small portion length here, delta L, the B is in this direction. B is parallel. So according to Ampere law, it says the sum of the element length delta L times the magnetic field parallel to the length element. Okay, see here, sum of the length element delta L times the magnetic field parallel to the length element, that means B times, okay, is equal to mu naught I, equal to mu naught I, and it has to be a closed path, and this is a closed path. This is a closed path. So when you look at this, this is a closed path. Okay, alright, so don't get me wrong, this one I put time is based on the sentence, it's not a vector product. Okay, better I cancel after that, might be misunderstand. I try to put it into words. I'm trying to take the words and put it into a symbol here. So this will be the right one. So B parallel to delta L is equals to mu naught I. Okay, mu naught I. Okay, so then if you see in this portion, in another small portion here, if I take another small portion here, then here will also be delta L, and then here also be B parallel. And then I take another portion here, I keep on taking another small portion here, so here will be in this direction, it will be delta L and then B parallel. Okay, until you cover up the whole entire closed path. Okay, until you cover up the whole entire closed path, you will notice your total delta L will be 2 pi r. Your total delta L will be 2 pi r. Okay, and your B parallel is constant, the value is constant throughout the closed path. So therefore your B parallel to delta L will equals to B 2 pi r equals to mu naught I. So B is equals to mu naught I over 2 pi r. So this will be the formula. And this is a formula of magnetic flux density, which is at this point, r distance, okay, or a radius from the wire which is carrying the current I. So the formula will be B equals to mu naught I over 2 pi R. Okay, alright. Yeah. Alright, so that is one thing. And one more thing that I want to explain. Okay, let's look at the book here, the textbook here. Okay. Okay, so this is the concentric circle for this example. This is the conductor that is carrying the current. This is the concentric circle. The pattern is a concentric circle. So if you look at this pattern here, okay, hold on, yeah, you will realize that the separation between the magnetic field increases. The separation between the magnetic field increases as it goes away further from the conductor. So it says the separation between line of forces increasing as the distance from the wire increases. Okay, and this indicates that the field gets weaker as the distance from the wire increases. Okay, I just want to let you all know here. Now, if you draw a dot will represent the direction of the magnetic field. So if it's a dot, then the direction of the magnetic field is out of the page. Correct? Okay. But if you draw an X will represent the direction of the magnetic field into the page. Okay, into the page. But if you draw a dot and you draw a circle around the dot, that is a conductor carrying a current or current carrying a conductor. So this will represent the direction of the current, where the direction of the current is out of the page. Okay, and if you draw X with an dot, that shows the direction of the current in a conductor into the page. Okay, into out of the page. This is for conductor carrying current. Okay, this is for the direction of the magnetic field. That is the very reason why you see in this example of figure 16.8, they draw this small thing here. That means they are talking about a current carrying conductor. And then again they draw back the same thing here. They also draw with a small dot with a round shape. So you have to be careful when you draw any symbol to represent your example. Okay, then they say here, okay, this number 3 is about the direction of the magnetic flux density, which is using a right hand grip rule. And then they talk about Ampere's law, which is associated with the magnitude of the magnetic flux density, where this is very important because they want you to derive the magnetic field of a straight wire by using an Ampere law. So it says here what? Closed path. The key word is closed path. So if you realize here, this is a closed path. Closed path. That's why Ampere law is also similar to Gauss law. The sum of the length element delta L times the magnetic field parallel to the length element B parallel equals to mu naught I. Okay, so you get this. Okay, you get this. Alright, so then what is mu? Mu is called as the permeability of free space. Mu is called as permeability of free space, and the value is 4 pi times 10 to the power of negative 7 Henry per meter. Okay, H stands for Henry per meter. Okay, alright. So in this example, we have in figure 16.9, we have a current carrying conductor where the current is coming out of the page. Okay, so if I draw the concentric circle, I use my right hand grip rule out of the page, so my direction of my magnetic field will be in this direction. So that's why you see your B. Okay, now the suitable closed path is in the form of a circle of radius r. So the direction of the magnetic field B at all point on the circular closed path is tangent to the circle and the component of B parallel to the closed path. Okay, alright, so B is parallel to B, so therefore you solve this and then you get the formula. Okay, alright, so that is all, class.
For example number 2, circular loop, the learning outcome will be to use the formula for a circular loop.
Look at the magnetic field in a circular loop. The learning outcome is to use the formula. Okay, here is an example that I have shown you all. Okay, the magnetic field produced by a current in a circular loop. Okay, now I have a conductor. The current flows here, so maybe I can just imagine that there's a battery here. Okay, so the current flows here and the current flows here, flows in and then comes out. Okay, so we know whenever there's a current, there's a magnetic field around the current. Okay, so when the current flows in this direction here, okay, what happened is there will be a magnetic field line produced around the conductor. Okay, now how to determine the direction of the magnetic field line is by using a right hand grip rule, where the thumb will point to the direction of the current and then the fingers will point to the directions of the magnetic field. Okay, so you will get the direction of the magnetic field in such a way. Alright, and same goes to here. The current flows out. Okay, it look like as if the current is flowing out of the paper. Yeah, current flows out of the paper and going into the paper, so here it will be in this direction. So if you use your right hand grip rule, this is the direction of the current and then this will be the direction of the magnetic field. So that's why you get the direction in this way. Okay, so then here you will realize that as you draw the pattern of the field, you will realize that here is more stronger, at the center here is more stronger, the fields are more stronger because you can see the magnetic field lines are closer apart. Okay, they are very close here and they are more, the lines are more at the center. Okay, alright, so then how do we find the magnetic flux density? The magnetic flux density B is equals to mu naught. Okay, now what is mu naught? Mu naught is permeability of free space. Permeability of free space. Okay, and then times with N. Okay, N is the number of turns. Okay, so in this example the number of turns is only 1. So if you have many turns, then N will be according to the number of turn. But based on this example, N has only 1 turn in this example. Times with current, the value of the current here that flows, divided by 2R. Okay, 2R. And what is R? R is the radius of the coil, okay, which is from the center here, the radius which is from the center here to here. So this will be the radius. Okay, this will be radius. From here to here will be the diameter, and then from here to here will be the radius. Okay, alright, is it the center here? Okay, this is the center. Okay, alright. Okay, so this will be the formula to find the magnetic flux density for a circular loop. Okay, now let's look at our notes. Let's look at our notes. Okay, page 161 of our Oxford FAJAR book. Okay, it says here figure 16.10 shows the magnetic field produced by a current in a circular loop. The direction of the magnetic field may be determined using the right hand rule which is also called as right hand grip rule, because you grip, okay, also called as right hand grip rule. Okay, now they say grabs the left side of the coil with the thumb pointing out of this page as the okay, what's the most important thing? Thumb is actually pointing the direction of the current. The fingers will curl to the direction of the field. So thumb is the direction of the current, fingers will point to the direction of the magnetic field. Okay, so this is an example here. So in this example, this is the coil, this is the coil, okay, this is the loop, this is the loop. So here, if you see here, the current is flowing into this direction. So the current is flowing into the page. So when the current is flowing into the page, when I use my right hand grip rule, so it's into the page, so my direction of my magnetic field is in this direction. Okay, so I get here. Okay, and then if you see here, the current is flowing in and then flowing out of the page. So when it's flowing out of the page, at that particular point it's flowing out of the page. So this is the direction of the current, this is the direction of the magnetic field. So I get it like this. Okay, can you see that? See, look at the direction of my fingers and the direction of the line. Okay, all right, so R is the radius of the coil, so this will be the radius of the coil. Okay, N is number of turn. In this example also, the number of turn is 1 and I is the current. So magnetic flux density at the center of the coil is B equals to mu naught Ni over 2R. Okay, alright, so that is about circular loop. So you have to learn how to use the formula. Questions will follow.
For the example number 3, we are going to learn how to use the formula for a solenoid. Before we learn to use the formula, let's understand the concept of a magnetic field due to current of a solenoid.
This lesson is about magnetic field due to current in long solenoid, and we're going to learn how to use the formula B equals to mu naught Ni for a solenoid. Okay, now what is a solenoid class? Solenoid refers to a long thin loop of wire, long thin loop of wire, okay, often wrapped around a metallic core. But here we don't have a metallic core, we're just going to talk about air core. Okay, because now they are very effective because they can create control magnetic field, they can create control magnetic field, and can be used as an electromagnet. Okay, now I have a solenoid here. In this drawing here, I have a solenoid here, and okay, let me take out some few pens here. Okay, they are made of thin wires, alright, thin long wires, and then they are looped. Okay, so you see here we have thin long wires and then they are looped all together. And this thin long wire, we can imagine that they are actually fixed to a power supplies like this, and then current is flowing into the wire, current is flowing in the wire, not into the wire, current is flowing in the wire. After that it goes on like a loop, the current flows in the loop, and then the current goes back to the power supply. Okay, now here when we talk about the magnetic field due to current in a solenoid, we are going to look at first, when we talk about magnetic field, we know magnetic field is a vector. Okay, magnetic field is a vector. We need to know about direction and also magnitude. So for the first starting, we are going to talk about the direction of the magnetic field. Okay, the direction of the magnetic field. So we know whenever there is a current flow, there's a magnetic field around the conductor. Okay, now when we draw the pattern of the magnetic field, this will be the pattern of the magnetic field. Okay, now the magnetic field lines are never crossed to each other. These blue lines are called magnetic field lines. They are called what? They are called as magnetic field lines. Okay, they never cross, and the magnetic field at any point is very unique. That means the magnetic field here and the magnetic field here and the magnetic field here, they are very unique, okay, in their values. All right, magnetic field line are continuous. They are very continuous and they form closed loop without beginning or ending. Okay, all right. So current in solenoid produce a stronger magnetic field inside the solenoid than outside. All right, current in the solenoid produce stronger magnetic field inside the solenoid than outside. So before we go to that, let's look at the direction of the magnetic field. We know the pattern of the magnetic field is such that how to determine the direction of the magnetic field. There are two ways of determining the direction of the magnetic field. If you look at your Oxford FAJAR book in page 163, our textbook, now there are two ways. The first way is by looking at the North Pole and the South Pole. Alright, by looking at the end of the coil, look at the coil from the end concerned. Okay, so here if I look at the coil from the end concerned, like say for example in this figure 16.11, so I make sure I come to the end of this solenoid here and I look at the end concerned here. Okay, my eyes have to be this side. So when I look at this, I will realize that the current's flowing direction is this side. Okay, current flowing direction is this side. So this is already anti-clockwise. So when it's anti-clockwise, that means this is north. The current flow direction is anti-clockwise. Okay, current flow direction is anti-clockwise. So this is a north. Okay, then if you look up at to this end here, you make sure you look up at this end here, you will realize the direction of the current is this side. So this side means is clockwise. Okay, it's clockwise. So the current flow is clockwise. So this must be south. Okay, so you can see here south, you can see here north. All right. So there's two ways here. One is by North Pole and by looking at the where is the North Pole and the South Pole. And then here, if it's a North Pole, then it is the direction of the current is anti-clockwise. Okay, but if it's a South Pole, the direction of the current will be in the clockwise at the end of the solenoid. Okay, you must look at the end of the solenoid. So this is the first method. The second method, which I'm very comfortable with, is called as a right hand grip rule method. Okay, now the first one was the north and the south. The second one, which I'm very comfortable with, is use right hand grip rule method. Okay, right hand grip rule. Okay, definitely you use your right hand. All right. Okay, right hand grip rule, you take your right hand. Okay, now this is one method, but this method I'm just going to clarify here. I'm going to draw a table here. Okay, now this method, if it is for current carrying conductor, or if it is for circular loop, then this right hand rule, right hand rule. Okay, you have it like this. I know my thumb looks more bigger. This is your thumb. Okay, in these two example, current carrying conductor and circular loop, your thumb actually represent the direction of the current. And your fingers represent the direction of the magnetic field. But in solenoid, okay, let me take my black pen. Okay, in solenoid, this is your thumb, this is your fingers. Your thumb represent the direction of, or represent to the North Pole. Okay, that will be the right word, to the North Pole. And your fingers here, it will represent to the direction of the current. It will curl up to the direction of the current. Okay, so like now if you see here, if I use in this example, right, current flows in here, current flows, so goes there. So the direction of the current is such. So I use my right hand grip rule. It's like as if I'm gripping. This is a solenoid. Like as if I'm gripping. My finger will curl up to the direction of the current. So in this way, in this example, you see my fingers is curling up to the direction of current. Current is this side, right? So I curl up to the direction of current. Okay, so it's like this, as if I'm holding the solenoid. Is like this. So I grip it. So this thumb will point to the direction of the North Pole. So here will be north. So if this is north, this will be south. So the magnetic field will go from the north to the south. So you can see the magnetic field line, pattern line. So it will go from the north to the south. Okay, it will be like that. Okay, so that is about the direction of the magnetic field. Okay, now let's look at the magnitude of the magnetic field. Okay, number 2, B, magnitude of the magnetic field. Okay, now the magnetic field is uniform inside a long solenoid. So you can see it's very uniform. Okay, now there are values where the magnetic field inside the solenoid, when I say magnitude of the magnetic field, means I'm talking about the magnetic field strength or the magnetic flux density. It's the same. So the magnetic flux density inside the solenoid, okay, now the value will be B equals to mu naught and I. Now this will be at the center of the solenoid. So the magnetic field flux density will be around here, will be B equals to mu naught and I. Now what is mu naught? Mu naught is the permeability of free space. Okay, permeability of free space. And what is N? N is number of turns per unit length. The number of turns of the coil per unit length. Length is from here to here. This is length. Okay. And I is definitely is a current. Okay, so the magnetic field strength or magnetic flux density at the center of the coil, which is the strongest, it is B equals to mu naught and I. But the magnetic field at the end of the solenoid, which is here, will be half of what is inside the solenoid, will be half of B, which will be half of U naught and I. Okay, all right, so that shows the magnetic field line spread out at the end. It's spread out and it is weaker compared to the center. Okay, all right, so let's look at our notes here. The magnetic field is uniform inside a long solenoid. The magnetic flux density within the solenoid depends on the current. Okay, it depends on the current and number of turns per unit length. Okay, is N. So it is given by the expression B equals to mu naught and I. The magnetic field line spread out at the end of the solenoid. So that shows the magnetic flux density at the end is weaker. Okay, so the magnetic flux density is half of that within the solenoid. So at the end of the solenoid is half of what is in the center. Okay, all right, so from here, how do we increase B? Our next question. This is number 1. We talk about magnetic field. Okay, number 1, we talked about what? Magnetic field. And since magnetic field is a vector, we want to know the direction and then we want to know the magnitude. Next, we want to talk about is number 2, how to increase B. Okay, now we want to increase B. We want to increase the magnetic flux density. So how do we increase the magnetic flux density? First thing, to increase B, we can increase I. By looking at the formula, we can increase B by increasing the current that flows in the conductor, in the solenoid. Okay, number 2, this is 1. This is number 2. Number 2, we can increase B by increase the number of turns. Okay, we can increase B by increasing the number of turns. Because why? Here, if you increase the number of turns, you increase your B. Okay. Number 3, the third one. We can increase B by increasing or by winding it into a soft iron core. Okay, by inserting, the right word is by inserting a piece of a soft iron inside the solenoid. Okay, by inserting a piece of soft iron inside the solenoid. Okay, like say for example, I have a diagram here. Okay, you can see there's a 2 diagram here. Now this diagram in the core, it's air. This diagram in the core, it's a iron. Okay, it's an iron core here. This is an air core. Iron, this is an air. So if you look at the magnetic field lines, you realize that the magnetic field lines here are lesser compared to here. Here are more. The magnetic field lines here are more. So that shows the B here is less than the B here. Okay. So that shows that when you put an iron core, you increase your B. Okay. Now, air core, when there's an air, the value of B will be mu naught and I. Okay. Mu naught and I. B equals to mu naught and I in the within the solenoid, or we say the center of the solenoid. But in the iron core, the formula will be B equals to K mu naught and I, where K is equals to mu R, where mu R is called as relative permeability of soft iron. Okay, like say for example, the value of mu r for soft iron is 5000. Mu r for soft iron is 5000. Okay, so if you count and see, if it's an iron core, B equals if it's an air core, B equals to mu naught and I. But if it's a soft iron, B is equals to 5000 times mu naught and I. So you see how much it is increased. Okay, all right, so that is the ways how to increase your B. Okay, so you see your notes. When a piece of soft iron is inserted into the solenoid, the flux density within the solenoid is given by this. Okay, where mu r is the relative permeability of soft iron. Okay, the value of mu r for soft iron is 5000. Hence, placing an iron bar inside a solenoid increases the magnetic flux density. It increases the strength of the magnetic field. Okay, all right. Okay, so that is the lesson here. Number 6 is just telling you about, this is the solenoid. Okay, this is the solenoid. Within the solenoid, the B is higher, the B is more stronger inside the solenoid, and then at the end of the solenoid, the value of the B will be half of what is inside the solenoid. So that is what they're trying to explain here. All right, so thank you, class.